in the delta 1600.
Book is by Dan Carman on strangeness electroproduction at CLAS and CLAS12. You want to try to share your screen, Dan?
Yes, I am doing my best here. So you should see something now.
We do. If you can go full screen. Perfect.
Go. All right. So thank you everybody for having me, and I look forward to sort of sharing my perspective from the experimental side on topics related to what Jorge just talked about. But there's sort of a fancy looking title here, but really what I wanted to cover in particular was what we call the N-STAR program in Hall B at Jefferson Lab. And this program has a long history going back to the mid to late 80s when it was first dreamed up. And you know, we had this CLAS spectrometer. We went through a very long program, and I'll talk about that. And that's led to the 12 GeV era and a continuation of this program and very exciting prospects for the future with CLAS12, this new large acceptance device. So by way of at least a brief outline, I'll talk about at least set the stage for why we're studying the spectrum and structure of these excited nucleon states. I'll try to make it relevant for the sort of main goals of this workshop. I'll highlight some of the measurements that we have achieved in electroproduction for final states like single pion and 2 pion. And the reason why the strangeness electroproduction is in the title, because that's sort of where I've been sort of turning the crank. But I want to use the non-strange channels to sort of set the stage for why the strangeness channels are important. And then after I sort of talk a little bit about some highlights from CLAS, I'll set the stage for CLAS12 and the N-STAR program, what we're working on and our plans for the future. So let me dive in to give you an overview of the N-STAR program in Hall B. So this program is really one of the key physics foundations of Hall B. It has been since its inception. We have these large acceptance spectrometers, CLAS and CLAS12. They're called for the CBAF large acceptance spectrometer and the CBAF large acceptance spectrometer at 12 GeV. They were designed to measure cross sections and spin observables over a very broad kinematic phase space for a host of different exclusive reaction channels. And I list here in purple just a sort of a subset of some of the channels that have been studied to date or are planned for the future. And sort of a motherhood statement, if you like, of our goal is to explore the spectrum of N-STAR states and their structure. To be a little bit more explicit, what we're trying to do is to probe the underlying degrees of freedom as a function of Q squared, and what we're actually measuring are these so-called electrocoupling amplitudes or electroproduction amplitudes. They're obviously derived from applying various models to try to explain the observables that we measure directly as experimentals, cross-section spin observables, and I'll say more about that in just a moment. Now, these different amplitudes, these electrocouplings, don't depend on the decay channel, but different final states have very different hadronic decay parameters and backgrounds. So we're studying different final states to really sort of come to grips with how well controlled the systematics are in these extractions, and the results are quite impressive already, as I'll show. Now we gain insight into the emergence of hadron mass by mapping the Dress-Quark mass function from the results on the electrocouplings for different excited nucleon states. And the last thing I'll say here in sort of introductory mode is that these data can unravel and reveal the spectrum of contributing states in a manner complementary to photoproduction. So I'll say a few words why electroproduction is really sort of a different way to look at the spectrum of produced N-STAR and delta star states. So as I said, CLAS had a very long program. In fact, we took data in the range from sort of 1997 to 2012. We decommissioned the spectrometer in 2012, and we were sort of off the air for several years while we sort of removed the old equipment and installed CLAS12. And CLAS12 began taking data in 2018. So I'll say a few words on that. But for CLAS, I wanted to give you sort of an overview of what we've done experimentally in terms of measurements in the nucleon resonance region. And so these are all of the papers that we have published as a result of this program with CLAS over the years. In the different colored boxes, I sort of grouped together the measurements from the different exclusive reactions that we've studied. So you can say things like 2 pion, various single pion channels, eta, strangeness, obviously is what I'll be talking about today, mostly, omega, rho, and phi. I show here the observables that we've measured, whether it's cross sections, spin observables, polarization observables, whatever you want to call them. The kinematic range, so it spans the full nucleon resonance region. And with CLAS, we had electron beam energies up to 6 GeV. And so Q squared, we had to reach sort of anywhere between 4 to 6 GeV squared, depending on the final state. And then just for completeness, I include the publication reference. So if you're interested in sort of digging into this a little bit more, this is sort of a complete list. Now, complete list, this is sort of what we've done to date, but I should say these tables are not yet frozen because we're continuing to mine the data that we've collected with CLAS, and there'll be additional measurements coming out and a number of these different channels to sort of continue to extend what we've been able to get out of the program with CLAS. So that's there's still more for the future. Now, given that, let me sort of come into a little bit more of an explanation of why we're sort of interested in studying excited nucleon structure and sort of how we go about this. So, from my standpoint, I like to think that nucleon structure is more complex than what can be described accounting for quark degrees of freedom only, sort of moving beyond what, I learned as an undergraduate back in the day. Things are definitely evolving in terms of how we understand nucleon structure. So you just heard Jorge talk about this a little bit, but there's sort of different regimes that we look at low form momentum transfers, say below about 2 GeV squared or so. The structure is well described by adding an external meson cloud to the underlying inner quark core. But as you go to higher Q squareds and higher Q squareds, and for this argument here, it's sort of roughly 5 GeV squared and above, the quark core is really dominating. We're sort of studying the transition regime from confinement to perturbative QCD. So it was essentially, as we slide along this Q squared axis from low Q squared to high Q squared, the dynamical picture of the nucleon is changing, and that's what we're trying to map out. And what we map out is the extraction of these so-called electrocoupling amplitudes or electrocouplings. And they're described in this cartoon picture by this red vertex, where I have a virtual photon interacting with the proton of the neutron and exciting it into an N star or a delta star. And so that's sort of what we're probing, is that vertex there. And what we talk about as a particular basis for these electrocoupling amplitudes are the so-called helicity amplitudes. And there are 2 transverse amplitudes, A1/2 and A3 halves. And then there's a longitudinal amplitude called S1/2. And sort of the cartoon picture at the bottom sort of shows you what I mean by spin 1/2 and spin 3 halves. Now, these electrocoupling amplitudes is what we're trying to measure as a function of Q squared. As sort of, really the only source of information on many facets of the non-perturbative strong interaction and the generation of these excited nucleon states from quarks and gluons. And the momentum dependence of the rest quark mass function sort of shapes the structure of these states in their Q squared evolution. So it's sort of the connection to sort of, going from, sort of more humble observables like cross sections and spin observables to sort of the underlying dynamical information is through these electrocoupling amplitudes. And that's sort of our connection to ultimately, Dyson-Schwinger approaches or ultimately lattice QCD when we get there. So I want to say a little bit about some features of the data. I'll begin with a couple of highlights here. These are just representative examples from a much broader set of results that have come out, but I'll focus here on, in particular on lower lying N star states. And I've shown here the A1/2 electrocoupling as a function of Q squared from analyses of CLAS data. And the Q squared range, if you can read the axis, goes, it's a common for all plots, it goes up to sort of 4 to 5 GeV squared. And I show on the left the Roper, the middle the 1520, and on the right the 1675 sort of representative examples. And the 2 plots on the left of the screen, the Roper and the 1520, we focus on those black curves. They come from a light front relativistic quark model, and they're sort of expected to be valid sort of as you go to higher Q squared, where you're probing the quark core. But at lower Q squared, we have this very important effect of the meson cloud. And the way you sort of infer the relevance or the strength of the meson cloud is looking at low Q squared, the difference between, in this case, the relativistic quark model and the data. And so that's sort of those shaded bands labeled meson baryon contributions. And what's interesting, of course, is if you compare for different states, sort of the evolution of that meson baryon cloud as a function of Q squared, you see that there's a very different interplay between that meson baryon cloud and the quark core, which is why we want to study different states. The thing that's also relevant here is that there are 2 sets of data that are highlighted on these plots. The red data points are from analysis of CLAS single pion data, and the green data points are from analysis of CLAS charged 2 pion data. And these analyses are completely independent of each other, but you see that there's very good correspondence between these different sets of data, which gives us really compelling evidence of the reliability of these results. So this very important structure information. These channels, the single pion and the 2 pion channels, have a very different mechanisms to the underlying non-resonant background. So this is a non-trivial agreement. And one of the things I think is important is, these data that we collected with CLAS are beautiful, as you can see that they are. But with CLAS12, we're taking data with an order of magnitude higher beam target luminosity. And as we move into the future, we'll be covering this kinematic range with CLAS12, but we'll be able to provide more precision studies with much improved measurements. Now, of course, CLAS12 will go beyond this kinematic range. We'll ultimately, with CLAS12, beam energies up to 11 GeV, be able to sort of reach Q squareds in the range from 10 to 12 GeV squared, sort of the highest we've ever been able to probe and these sorts of exclusive reactions. So we'll overlap what we've done with CLAS with much better precision, and we'll definitely extend the kinematic reach. And I'll say more about that in just a moment. Now, just a few words on higher lying states, and this will sort of set the stage for introducing the strangeness channels. But the 2-pion channel is sort of the dominant part of the cross section for the upper end of the nucleon resonance region, and it's given us the first electrocoupling results on states up to about 1.8 GeV. Now, most higher lying end star states decay mainly to 2-pion with much smaller strength n pi. So one of the strengths of, or way we've been able to make so much progress over the last 10 years is by extracting electrocouplings from 2 independent channels and making sure we have correspondence and agreement. That way we can understand the systematics. But now as you go to higher masses, you only have really sort of the 2-pion channel right now. And you don't have that sort of second channel to compare against. And that's exactly where the KY channels come in. The threshold is at 1.6 GeV, and so they're naturally sensitive to the upper end of the nucleon resonance region. And so the future is to be able to extract electrocouplings from the KY channels in comparison to the 2-pion channel. And what I show here are just some examples of electrocouplings from analysis of 2-pion data from CLAS. There's the S1/2 for the delta 1620 on the left, the A1/2 for the delta 1700 in the middle, and then the A3 for the 1720 on the right. So to sort of drive this home a little bit more, the data from the KY channels is critical to provide that independent extraction. And they'll also be important to elucidate the possible impact of 3-quark orbital excitation on the emergence of hadron mass. So we look forward to sort of moving this forward. But there are some caveats, obviously, if we're going to use the strangeness channels to extract or get to the structure information. And I'll cover that in the next several slides. Now, let me say a little bit more to sort of bring this to relevance for this particular audience, this particular workshop. This slide is entitled Emergence and Distribution of Mass. And we've already seen this sort of picture on the lower left corner, more of sort of a textbook picture from, sort of a cartoon, but it's actually, quite a compelling picture that shows the effect of quark mass in a baryon as a function of the quark momenta. And so you see it's obviously not flat. There's a running to it. There's a momentum dependent to it. And which scale you look at, you're sort of looking at a sort of very different object. So at very low momentum, we're talking about constituent quarks. So our proton is 2 up quarks and a down quark. Each of those quarks is some 300 MeV object. So that's a dressed object. But as you go to higher and higher momentum, you're looking closer and closer to sort of a bare quantity. And the momentum that you're probing this at, the Q square that you're measuring the reaction at, you're sort of looking at things in a very different regime. And so with CLAS12, I've kind of put this sort of gray box on top of the picture. And I want you to be impressed by the fact that CLAS12 covers a very broad kinematic range to sort of understand exactly, and this this sort of very broad Q squared range, the dominant part of how hadron mass is generated. And as an example to sort of follow up a little bit more, I've put some pictures here in the upper right of the plot. Calculations of form factors and the electrocouplings, which are sensitive to the underlying dress quark mass function. This is the magnetic transition form factor for n to delta as a function of Q squared GM star. And for the 1440, I showed you the data before, but this is the same A1/2 electrocoupling as a function of Q squared. And there are 2 different DSC calculations overlaid here. The one is a red dashed line, and that's a computation assuming sort of a frozen quark mass. And obviously you can see that sort of in the range of above 1 to 2 GeV squared. That doesn't correspond to what we actually see in the data. The way you get the correspondence is, of course, and this is sort of where we're coming from, is including a running quark mass, you get the blue curves. And I should say that these calculations that I show here for the n to delta and the N1440 are using the same dress quark mass function for both calculations. You can see the level of agreement is quite impressive. That sort of gray region that you see on sort of the left of each plot is sort of where you have these other contributions beyond just the quark core. And so you really don't want to look in that regime for correspondence. It's sort of above that, sort of the range of 1 to 2 GeV. And sort of the fascinating thing for me is, by measuring sort of, these humble experimental observables, cross sections, and spin observables, we're really probing sort of fundamental questions in nature. What's the nature of confinement, and how is most of the visible mass in the universe generated? So it's very exciting to sort of, have that the ability from our measurements to sort of be able to probe these deeper questions, which are fundamental to our understanding of nature. So those are some sort of details on structure. Let me just on a single slide say a few words on the spectrum side of it. So in the upper right here, I show a picture from the constituent quark model. This is just an example, sort of showing the expected spectrum of states from this particular model. And I could have shown made some statements from lattice QCD, and qualitatively they would be very much the same. So this is just sort of to guide the discussion. But you see for the different spin parities, the predicted states are shown in each column by the blue lines. And then what we know from experiment is shown by the boxes. And the height of the box is something about the width of the state. But sort of up to about 1.7, 1.8 GeV, and there's very good correspondence between the expectations of the calculation or the model and what we see in data. But in that sort of red box region, the upper end of the nucleon resonance region here, it extends up 2 to 3 GeV. You see there's a lot of blue lines with nothing next to it. So it's really a vast area where we don't have huge amounts of knowledge. And the vernacular, this is called the missing n-star states, or the region of missing n-star states. So we're interested in sort of using strangeness channels to continue to extend our knowledge of the spectrum of n-star states in this region, and not just for stamp collecting. I mean, this is really sort of getting us to sort of understand QCD, and the spectrum of states that come out is non-trivial, and so that's why we want to continue to push this. Now, the table on the left side of this slide shows you sort of how, this is just about a dozen or so states in the particle data group, how our understanding or knowledge of them has changed over the past 10 years. So there's a column labeled PDG 2010. You can look even before 2010, and they kind of look very similar to this. And then PDG 2020 is from the most recent version of the PDG listing. So you can see that all the states that I've included here have either gone up in star rating, 3 to 4, 2 to 4, 1 to 2, et cetera. Or if they had no stars, they now have, some of these have 3 and 4 stars. So there's been a dramatic change in our understanding of the n-star spectrum, just even in the last 10 years or so. And one of the main reasons why this has come about is because of studies of strangeness channels, and particularly the photo production data from CLAS, gamma p to k plus lambda, gamma p to k plus sigma 0, have been very, very important to sort of give us this additional knowledge. And so, most people tend to think that, photo production is sort of a better way to go about, spectroscopy than electroproduction. In fact, people tend to think, well, electroproduction is really sort of for the structure side, photo production is for the spectroscopy side. And I think we need to think differently about it. Because certainly with electroproduction, we're basically can carry out analysis in different bins in Q squared. And we better get the same information in each bin of Q squared in terms of the information on the states. So we basically have many measurements that we can do in a single experiment to make sure that we have good correspondence. We're getting out the same information. So we want to use electroproduction as a cross check, if you like, of photo production. And once we start getting into the precision measurements with CLAS12, that will be a boon. And we also want to use electroproduction to continue, as I said, to sort of push into this sort of red box region where the missing n-star states are showing up. Now, just a quick flash of what we've done in the strangeness channels with CLAS before I get to CLAS12. So this is sort of a history of what we've done with CLAS measurements and KY electroproduction. We've taken data, beam energies up to about 5.7 or so GeV, and down to 2.5 GeV. And the data sets, you can see they go from blue to green to brown in the table, and that's sort of going from the earliest days to the later days. So typical experiments, we're collecting about 5 billion triggers or so. And the data that are sort of shown on the screen here represent really the world's data in this channel. CLAS completely dominates the landscape. So we've measured cross sections, differential cross sections, structure functions have been extracted. We've done Rosenbluth separations. We've measured fifth structure functions, beam recoil transferred polarization, recoil polarization. So we've covered a lot of different measurements in electroproduction, and the data is quite beautiful, as I'll show on the next slides. But this sort of is a complete set of references. And this is one of the measurements that came from this in 2013. We measured the differential cross sections for the electroproduction of K plus lambda. And from those differential cross sections, we can do a moment analysis in this angle phi between the electron scattering plane and the hadron production plane and separate out the individual contributions that form this overall cross section. We have this sort of combination of sigma t plus epsilon sigma L in the top row, and then the various interference structure functions. Shown here is a function of W, and each of the different columns is a different bin and the center of mass angle of the kaon. So back angles on the left, forward angles on the right. So these data were acquired at 5.5 GeV, and I'm showing here of the 3 Q-squared bins that we published that this is the lowest Q-squared bin. So again, this represents the world data. So this is what we have right now, and I should say that these data are of comparable statistical quality as the class 2 pion data. And I'll say more about that in just a moment, but I want you to appreciate how good these data are and what their potential is, sort of moving beyond this to sort of getting to the electrocouplings and the structure information. There are several calculations that are overlaid here. I don't want to go into huge amounts of detail due to time, but they're single channel models. The red model is sort of a traditional isobar model, and the blue model is a sort of a hybrid Reggie plus resonance model. These models were constrained by the photoproduction data. Nothing has been constrained in electroproduction, but you can see that they don't describe the data really anywhere in this phase space. So they really are not, sort of appropriate to consider as an extraction tool at this point. So that's sort of the state of where we are. And these are the corresponding structure functions from that same paper for the K plus sigma 0 final state. So very nice data. We just don't have the ability to sort of describe them theoretically quite yet. Just a few words on reaction models to sort of set the stage for one of my main messages from this presentation. In the top of this slide, I sort of list the main workhorses to sort of attack the single pion data, the pi plus n and the pi 0p data, to extract the electrocouplings. We typically use either fixed T dispersion relations or what's called the unitary isobar model. And these have a very long history and have been used on a number of different fronts. My colleague Victor Mokayev has been leading the development of what's called the JLab Moscow model for the extraction of the electrocouplings in the 2 pion channel. And that model has evolved over the last 15 or so years and has led to some very nice sort of discoveries, if you like, within the 2 pion data. That I think the most recent publication we had was last year with the discovery of a new N prime 1720 state that emerged from looking at the 2 pion data through this model. So the other thing that's left over, of course, for this is a KY reaction model. You'll notice it's highlighted here in red as opposed to the other ones in blue because I want it to stand out. It represents sort of, in my mind, the missing link. At present, we don't have a reaction model that adequately describes KY electroproduction data in the resonance region. And we need such a model if we're going to move from the experimental observables to the underlying structure information. And these data are certainly of sufficient quality from what we've already published to be able to do this. And we're continuing to push and try to work with partners to sort of develop such tools, but we need them, we desperately need them. And of course, with class 12 data coming out with precision, it will become even more important. So I include a reference here of a review article I wrote with Victor Mokayev and Kyun-Sun Ju that was published last year that sort of goes into some details on the different reaction models and their status. So if you're interested, you can see that reference. And my last bit here, I'd like to say a little bit about the future, class 12 and the measurement program with class 12 in terms of the N-STAR program. So we have a number of approved experiments at beam energies 6.6 and 8.8 and 11 GeV. Spanning really a very broad range of Q squared from essentially quasi-real photoproduction up to sort of 12 GeV squared. So this is really a whole new range for us. Span full nucleon resonance region. Obviously, it's large acceptance, so we're covering the full center of mass angular range of the decay mesons. And I list here just the titles of the different experiments. So the first 3 are sort of traditional studies of 3-quark baryons, if you like. And we also have an experiment that Victor Mokayev referenced a little bit earlier in the session to search for hybrid baryons with class 12. These are gluonic hybrids. And to sort of give you an idea of where we are at with class 12, so I mentioned earlier that we started taking data just a couple of years ago. This is 2018 is when the measurement program started. And as part of these 4 different experiments, we've already collected a little bit of data. To be more explicit, we've taken data sort of at, this is sort of the 11 GeV experiments, really it's 10.4, 10.6 GeV data. We've taken data in spring of 18, fall of 18, and spring of 19, and this amounts to about 50% of the total approved program advisory committee time. And the data from the experiment at lower energy, and we actually took data at 6.5 and 7.5 GeV. We had an opportunistic chance to get on the floor, so we got to sort of a splash of data over several weeks, which amounts to about 10% of the total program advisory committee approved time. The lower energy data is nice because the resolution is the best there to separate lambdas and sigmas, which are obviously only 80, 90 MeV apart. And so what I'll show today is actually featured from this sort of splash of data, which is already more than we've collected so far with CLAS. So I don't want you to dismiss the small amount of data because it's beautiful. And just a quick remark, the first two analyses from CLAS12 papers were submitted in January of this year. So the door is open and we're starting. The papers are on semi-inclusive deep inelastic scattering beam spin asymmetries, single hadron and dihadron production. So those first two papers are out the door. One's been accepted and the other is under review right now with the referees. So that will be very nice. But this is sort of just the starting point for the number, sizable number of publications that will be coming out over the next few years. I've listed here just a few remarks to sort of the goals of these programs in 12 GeV, studying higher lying N-star states, understanding the effect of the meson cloud and N-star structure, probing the dress quark mass function. So these are very fundamental to the program with CLAS that I already talked about, but also moving forward in this new kinematic regime with CLAS12. So just in my last few minutes, just a few looks at some of the data. And you can imagine with the brand new spectrometer that CLAS12 is, you don't just start off on a t equals 0 and extract cross sections. There's a lot of things you have to do before you can really make sure you can normalize yields in a brand new device like this. So what we've been working on is sort of going after, if you like, the low hanging fruit, which are beam spin asymmetries. And that's where we're starting here as well. So this is from that data that I mentioned from lower energy 6.5 GeV. This is the EK plus missing mass spectrum. So you see the lambda and the sigma 0. And the first thing that we're going to publish from this analysis is beam recoil transferred polarization. So that's extracted from a helicity asymmetry. And so I sort of show what things look like for the two components of the polarization that survive the way we do the analysis integrating over this angle phi here. And I present them in this coordinate system with the z prime axis along the KN and the x prime axis in the hadronic plane. This is K plus lambda polarization as a function of W. This is K plus sigma 0 as a function of W. And it sort of gives you an idea of, with this sort of 10% splash of data in this data set, what things look like. And I purposely not tried to go into any physics here. And in fact, these are not even final polarizations. I'm sort of just summing everything up within the blue band and within the red band. So there's background in here. Obviously, if I tried to show you something more refined, I'd have to go through more of an approval process within the collaboration. We're not there yet. This gives you an idea of the statistical quality of these data. And the way I want to make the comparison is to show you the world data. This is what we published from CLAS. This is data that was published in 2009. Similar kinematics, beam energy of 5.75 GeV. This is the world data for K plus lambda transferred polarization. This is the world data for K plus sigma 0. So you'll notice that the y-axis covers a much broader range. We have about 5 times more data in just this little splash of data. So already very exciting. This is the world data for beam recoil transferred polarization for K plus sigma 0. It's almost useless. You can barely even tell the sign of the polarization. Now you can see what we can do with CLAS12 from just this tiny little splash of data. So already it's very exciting in terms of what we can do. And obviously, as we get the rest of the data at this beam energy in the next few years, obviously we'll be able to be talking about precision measurements. And the last the thing I want to show in terms of a quick look at the data, we've been measuring sort of as a proving ground for how to normalize yields, data from 11 GeV, looking at an inclusive electron scattering cross section. So we can compare against world data where it exists at sort of lower Q squared, and then sort of go to sort of the new kinematic phase space where we have very broad coverage in Q squared and W up to sort of in the range sort of up to sort of 10 GeV squared or so. So it's more than just sort of utilitarian. These inclusive cross sections also allow us to gain insight into ground state nucleon PDF in the resonance region, and insight into quark hadron duality in the resonance and DIS regions. But that's sort of the starting point for cross sections as inclusive. But I've also taken this a little bit farther from the same data set at 6.5 to extract. These are essentially cross sections, but listed as arbitrary normalization because I haven't done things like radiative corrections yet. And these are still preliminary, obviously, but it gives you a sense that even with a small splash of data, we have very fine bitting in Q squared and can extract these differential cross sections. So that's sort of what will come up after we get the polarizations out the door. So it's not quite fully impressive yet, but stay tuned. We're getting there. So we have some short-term plans in the KY channel measuring beam spin asymmetries and polarization, and the cross sections will sort of be 2 to 3 years from now. And I'm focusing here on strangeness, but this work that I'm showing is really part of a bigger program in the NSTAR program with CLAS and CLAS12. So we have active analyses on inclusive electron scattering, single pion, two pion, beam spin asymmetries, differential cross sections. And I just sort of like to give an advertisement. I'm not sure it's been mentioned yet in this workshop, unless I missed it. But we have this strong QCD workshop that's hosted by Craig at Nanjing virtually, June 7th to 10. And there'll be a lot more discussion on these ongoing measurements from different aspects of the NSTAR program. So my final slide, really the NSTAR program in Hall B is one of its key physics foundations. And we've been doing this for quite some time, and it's very nice to sort of see what's coming out and get excited about the future. So we've already made a huge amount of progress understanding electrocouplings and structure for states up to about 1.8 GeV. We want to continue to extend that. CLAS12 will obviously have a much broader kinematic range, but the exciting thing is in the low Q squared end, sort of up to 2 to 3 GeV squared, we'll have statistics in electroproduction comparable to photoproduction for the first time. So that's what I mean by precision measurements. So these studies from CLAS12 will probe the Q squared range where the dominant part of hadron mass is generated. And they'll be an important addition and input to address the most challenging problems of the standard model on the nature of hadron mass and confinement and the emergence of NSTAR states from quarks and gluons. So I'll end here and see if there's any questions out there.
Thank you, Dan, for this nice overview. Any question?
May I ask?
I see, Craig,
Do you observe the change of the nuclear mass on the quark mass? If yes, can you show this dependence?
So, I mean, what's the point of the question? Let me ask it from that standpoint, so I can tell you how I want to answer it.
Do you observe the change of the nucleon's mass on the quark mass? If yes, can you show this dependence?
No, not yet. So stay tuned. Let me put it that way.
Not observe.
Craig, do you want to speak?
Yes, thank you. Daniel, thank you very much for that. I'm very excited by the possibility that we'll have electroproduction form factors for transitions to states carrying strangeness. We have very little to constrain the behavior of the strange quark mass function. We have poor data on the kaon form factor. So if you can extract precise data on the electroproduction of states with strangeness, then you'll be providing us with the first really tight constraints on the behavior of strange quark mass generation.
Yeah, thank you for that comment, Craig. And that's sort of one of the reasons why myself, along with my colleague Victor Mokeyev, have been sort of pushing this, to looking for someone to work with, sort of develop this extraction tool. That's sort of the next step for us. And so we'll continue to push that. I'm sure we'll be talking more about this at your workshop in June.
Victor, you want to comment on this question, or do you have an independent question?
Just complimentary comment. It's not question. Actually, Daniel already mentioned importance of reaction model in order to extract nucleon resonance electrocoupling. I want to emphasize that this is very needed, but just part of the work. Another part of this work, we need the approaches capable to relate phenomenological information on nucleon resonance electrocoupling to strong QCD dynamic underlying the generation of excited nucleon states, and see how this dynamic emerged from QCD Lagrangian. And in this way, all our group is very impressed by really breakthrough achievement achieved within continuum QCD approach by international group under Craig leadership. Right now, for the first time, they predict Q-square evolution of electrocoupling of several excited nucleon states, starting from the QCD Lagrangian. Right now, we are verifying prediction, solid prediction for electrocoupling of delta 1600 free half-plus resonance, obtained starting from the QCD Lagrangian within a framework of continuum QCD approach. Right now, continuum QCD approach only available, capable to describe Q-square evolution of resonance electrocoupling. Other approach are welcome, and we expecting their contribution.
Thank you for that, Victor. Nice comment. Thank you.
George, do you have a question?
Yes, thank you. Thanks, Daniel, for the nice talk. Could you please go to the slide 12? Thanks. I think that is going in the same direction than Craig. So what you are telling us is that there is a problem or an issue with having a reaction model for the Kaon hyperon, in the sense that have you looked at Argon-Osaka coupled channel calculations, if they are including these kinds of final state interaction?
So we certainly at the time I was working with Kamano before he left, and this was just when they were starting to sort of extend things to the electroproduction side. But we haven't gotten sort of the practical ability to use it as a tool yet. So it's exciting as a prospect, but it hasn't sort of, we haven't partnered up yet to sort of use that as a tool to extract this information. So that's something that's just one example. There are other examples where we've worked with other groups to try to sort of move this forward. But there's a little bit of a disconnect between the modelers or the phenomenologists on our side that we're trying to work through. So that's basically the best I can say for now.
Because I can understand, I think that you need this kind of Kaon hyperon reaction model in order to extract the electromagnetic form factors, for example, of the lambda 1/2 plus. Mm-hmm. Okay.
So to sort of stay a little bit further, so the last interaction I had with the folks in Argon-Osaka was some initial comparisons to electroproduction data that weren't quite as favorable as I would have liked. And of course, if the reaction model, if you like, doesn't describe the data, then you can't sort of move beyond that point. So there's some needed dialogue to sort of how we can improve the description, what's missing, which parameters sort of don't match what we've measured from the non-French that way.
Victor, you want to comment?
Yeah, George, Argon-Osaka model you mentioned include KY reaction channel, of course, in 8-channel coupled channel formalism. However, resonance electrocoupling within the framework of this model have been extracted so far for the resonance in mass range up to 1.5 GeV, basically for delta resonance and Roper resonance, not for other resonance. The reason for this, we can extend this model further up to 1.6 GeV, but after above 1.6 GeV, we run into difficulties. We have no experimental information on hadronic coupling between many open hadron production channels. For instance, pi n nucleon goes to 2 pi n nucleon. Pi n nucleon goes to K lambda, K sigma, and so on. That's why in order to move this model forward in the region covered by Daniel data, additional input from Argon-Osaka model is needed in order to incorporate in sensible way the interaction, meson-baryon interaction in the final state. This is the major problem. And for this reason, we consider together with coupled channel model, individual channel model, which parameterize all this effect and fit parameterized contribution to the data.
Okay, thanks, Victor.
I see no more hands raised, so we can enter the discussion part of today's meeting.